Hi, eSchool Gates. Welcome to eSchool platform. I'm called Remy, your math teacher. Today's lessons will be on integrations, calculus part 1. And in this lesson, we'll see how to solve integration using partial fractions. So let's kick off. For our concept, we need to remind ourselves that partial fraction defines 4 types. The very first one, type 1, we have linear factor. That is, when the denominator is composed of a linear expression. That is, we have a divided by bx plus c dx plus e. So, decomposing this, let me say equivalent, we have bx plus c plus b over dx plus e. We should remind ourselves that the degree of x at the top must be less than that of the degree at the bottom. For type 2, we have nonlinear, also known as the non-reducible factor. We have non-linear factor, which says that if you have an expression, any bx square plus c, we can decompose as ax quadratic times c, let me say b, over bx square plus c. But here we should remind ourselves that the degree of x first must be less, the degree of x at the top must be less than that of the bottom. And secondly, the denominator must be of or must have complex roots. B square minus 4ac must be less than 0. That is, the denominator must be composed of a complex roots. For the third type, we have repeated factor. Yeah, repeated factor says that if you have an expression like a over, let's say, bx plus c to the power 2, yeah, you have a over bx plus c plus b, we have bracket, please, equivalent, please, over bx plus c to the power 2. Yeah, if you have nth power, it means you are repeating the expression or decomposing the expression to the n terms. So lastly, we have type 4, which is long division, which remind us that here it has 2 cases. The first case says that the condition on the first case that the degree of x at the top must be equal to that at the bottom. That is, I can give you an expression like x squared plus 4 over x squared plus 3. Like this case here, you see they have equal degrees, and the second case, or the degree at the top must be higher than that at the bottom. Let me say x plus 2. You can see here we can use these 2 cases to define a long division by partial fraction. So in taking an example to characterize our concept given on the previous board, let's say, for example, we wish to integrate an expression like the integral of x plus 3 over x minus 1 dx is x minus 1 dx. So here we need to first of all know that what defines the rule will be by partial fraction, and the type used here will be long division, since they have equal degree of x at the top and at the bottom. So in that case, we use the basic algebra called the long division. We have the x minus 1. So by long division again, here we have our divisor. Here we have our dividend. So proceeding with the division, x divided by x, you have 1. You have here 1, please. So this divide times this, x, we have minus 1. Subtracting. So this is 0, please, 0. Then now this minus minus is that's a 4. So this will drop to 1 plus a 4 over x minus 1. So it therefore means that we're able to decompose this expression to this single Newton function. So integrating this function is sufficient for us to handle this single Newton. So therefore integrating our x plus 3 on x minus 1 dx is sufficient for us to just solve 1 plus 4 on x minus 1, coupled with our dx, a defined integral to work with. So again, integration is distributive over the mathematical operation plus. So we can linearly distribute our integral as integral of 1 dx plus 4, let's say integral 4 over x minus 1 dx, as you can see on the board. So again, we can solve again as plus 4, recognizing 4 as a constant out of the integral since it's independent of the variable dx. So therefore, integrating now the two terms, the first one is a constant, so integrating 1 with respect to x is x using the first concept of integration, and then plus integrating the second term, we use the recognition view, which says that if the numerator is the exact derivative of the denominator, our expression tends to be the ln of the denominator. So all we just need to do is to see how to differentiate the denominator. So differentiating the term here, differentiating x, we have 1. In differentiating 1, we have 0 by differentiation. So you see that the 1 at the top is exactly the derivative at the bottom. So therefore, our expression will tend to be the ln absolute value of x minus 1. As you can see, why the absolute value? Absolute value because of the condition of the ln property. Remember that the ln is can take only positive real values, excluding 0. So that is if you have ln x exists if and only if x is above 0. So that defines the domain of the ln function. So again, our integral is infinite, so we should not forget to include our constant of integration k. So that gives us the integral of our expression as given in the example 1. So we can have another view. Let's say example 2, for example. I can give you an expression like, let's say the integral of 1 over x squared minus 4 dx, as you can see. Here we should remind ourselves that to integrate such an expression, we need to first of all study the denominator. But we should not be tempted to say that this expression is of a nonlinear factor because of the square. So in order to distinguish it, we need to study the discriminant. So first of all, the discriminant b squared minus 4ac, since it's a quadratic expression. So we're going to have b is 0. Let me say our a is 1, our b is 0, then our c is negative 4. So replacing it here, we're going to have 0 minus 4 into 1 into negative 4. That should give us a 16. So we now say it's greater than 0, which tells us that the expression has real roots. So we cannot say it defines a nonlinear. So since it's having real roots, we can then decompose our expression as a difference of two squares, x plus 2 and x minus 2. So this gives us the two roots defined by our expression. So having a function like this, x squared minus 4, is sufficient to have x plus 2 and x minus 2. So therefore, we can now use this to come out with a partial fraction that will help us to subsidize the function. So therefore, by partial fraction, which is case 1, that's a linear factor. So we are going to have 1 over x plus 2, x minus 2. So equivalent to say is a on x plus 2, b on x minus 2. So we then need to just solve for a and b because this is decomposition. So we use normal LCM. So if we come over here to this side of the board, so by normal LCM, based on our expression, so therefore we can have as 1 equals to a into x minus 2 plus b into x plus 2, as you can see, where we have multiplied by a common factor x plus 2, x minus 2. So we can use, let's say, expanding ax minus 2a, bx plus 2. So if you want to compare the coefficient to solve for a and b, the coefficient of x0 equals to a plus b, you can call this equation 1. Then the constant term 1 equals to negative 2a plus 2b equals to equation 2. So we can again use either the elimination method or the substitution method to come out with our solution, or we can just say, okay, from equation 1, our a is equal to negative b. Then we substitute in equation 2. So 1 equals to negative 2 into b, negative b plus 2b. So that should give us 4b, no, please, 2b, or let's say 4b. I've summed already. This is positive, so that gives us 4b. So it implies our b will be 1/4. So directly telling us that our a will drop to negative 1/4. So our function drops to x minus 2, x plus 2, to be 1/4 a negative over x plus 2 plus 1/4 on x minus 2. So we can just have rearrange the function. We can just have this minus 1 on x is a 4, x plus 2. So integrating that function is sufficient to, so integrating, let's say, our f of x dx, where f of x is our defined function, is sufficient to just integrate 1 on 4 x minus 2 minus 1 on 4 x plus 2 dx. So since 4 is a constant, we have 1 on 4. We just have the integral of 1 x minus 2 minus x plus 2 dx, as you can see. So since the integral is distributed over the operation negative, we can share equally the integral. So coming over here, we can have our results. So coming over here, we can share it as 1/4 integral of 1 on x minus 2 dx minus the integral of 1 x plus 2 dx, as you can see. Now we use the recognition view. Since looking at the two expressions, we can recognize that if you differentiate the denominator, it turns to what we have at the top. So differentiating x, we have 1, and similarly differentiating x, we have equally 1 here. So our final integral becomes 1/4 the ln x minus 2 minus the integral, the ln x plus 2, close, since 1/4 is a common factor, not forgetting our constant of integration. So that gives us the solution to our expression. So as exercises, so for some of you, we can brainstorm as exercises. Integrate the following. I ask you to integrate the following. A, the integral of x minus 1 on x minus 4 dx. B, the integral of, I can give you 3x minus 2, x minus 2 on x plus 1 dx. And C, the integral of dx over x squared minus let's say the function minus 2. So thanks for listening.